Hello everyone, today we're going to be spending a little bit more time with sections A2 and A3, and we're going to be proving triangles are similar again using the side, 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 angle, angle, and side, angle, side theorems. This is going to be part number 2, which is going to be mostly example problems and not too much more conceptual learning. So let's start off with this first guy right here. It says, which of these 3 triangles are similar? And you need to show work. I have a hint for you that you're going to need to kind of work this through by making 3 different sets or 3 different pairs of triangles. If you take a look right here, I started off by making my set of LMN and then RST. When I was building my ratios, I found that I had one ratio of 5/6 and another one of 4/5, which immediately meant that they didn't match, and so I could end it right there, and that's going to be a big nope. Then I also did LMN and XYZ, which is the very first and the very last. These guys right here all produce the exact same ratio of 2/3, which means that is the perfect set right there. Our final ratio would have been RST, which is the middle, and XYZ, which is the last. And once again, I got one ratio of 4/5 and another of 5/6, and although those are very close, they're not exactly the same, which means that this is a big no for that one as well. Let's take a look at our second example right here. This is a story problem, which is going to up the complexity a little bit for some, but I want you to know that this is going to go very much the same kind of way. So right here, it says in the diagram, there's a scale drawing of a triangular roof truss. If you take a look, this is what usually goes on the top of the house. But if you look right here, you'll notice our units are in inches. So this is very small. The length of the 2 upper sides of the actual truss, which is what we're going to draw right here, are going to be 18 feet and 40 feet. There we go. The actual truss and the scale drawing both have an included angle of 110 degrees. You can see your 110-degree angle there, and I'm going to include it on the actual truss as well. Is the scale drawing of the truss similar to the actual truss? Well, we're going to see if we can kind of prove that they're similar. Now, you have 3 choices. Your choices are side, 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 angle, angle, and side, angle, side. We definitely have 2 sets of sides and an included angle. So we're going to be shooting for that side, angle, side situation right there. But we need to make sure that our sides are going to be proportional. Our angles definitely are congruent, which is fantastic. So we're going to set up our proportional sides. We're going to be setting up some ratios with our 10 and our 40, which is going to reduce really easily and quickly. And then we're going to do a similar type of situation with our shorter sides, which is going to be our 6 and our 18. Now this one reduces as well, but it's not going to reduce to the thing that we want it to be. Now, some of you may be concerned that I have mixed units. My 10 and my 6 are both in inches, while my 40 and my 18 are in feet, and that's okay. It doesn't matter. You can do the same kind of work by converting all your inches to feet or your feet to inches and setting up ratios, and you'll still find that they don't match. So this is going to work out just fine with the mismatched units, and our answer, no matter how you set it up, is going to be a big no, because our proportions don't match. Let's take a look at another one like this. This one is for a lifeguard. It says a lifeguard is standing beside the lifeguard chair on the beach. The lifeguard is 6 feet 4 inches tall and casts a shadow that is 48 inches long. The chair casts a shadow that is 6 feet long. How tall is the chair? And so we're going to see if we can figure this out. Once again, you'll notice that there's a mismatch of units. We've got some feet over here, we've got some inches over here, and we've got some feet and inches at the exact same time. Now, of all of these mismatches, the only one that I am concerned about is this one that is a mix of both at the exact same time. Having feet and inches for your 2 different drawings is no big deal, because we just saw that right here in our original roof truss drawing. But to have feet and inches in this exact same dimension is a bit of a problem. So we're going to work on that part first. So our 6 feet 4 inches right here is going to need to change. The way that I'm going to change that is by remembering that there are 12 inches in a foot. And so I'll convert my 6 feet down to inches, and then I'll go from there. So we're going to take our 6 and we're going to multiply by our 12. And we're also going to add on our additional 4 inches after that. 6 times 12 is going to be 72. Which means that the actual height that I'm going to work with for this lifeguard is going to be 76 inches. So I'll be getting rid of the 6 feet 4 inch right there, and I'm going to be using the number 76. Okay, now it doesn't matter that these are all in inches and these are all in feet. That's totally fine. The major thing is that you just don't have both of those units in the exact same dimension. Okay, let's build some ratios. I am going to be looking at side lengths here because that's how I'm going to determine my height. But the reason that I can look at side lengths and build these ratios is because these triangles are similar to each other. And this is an interesting fact. They're similar to each other because of angles. So if you look right here, the way that the lifeguard is standing on the beach and the way that the chair is constructed are going to be perpendicular to the ground. So we have a 90-degree angle in both of these triangles. Similar to that, but slightly different, is the sun. The sun is going to be up here in the sky, shining its light, and it is going to create a set of angles that are going to build shadows off of our lifeguard and off of our chair. And these angles are going to be congruent as well because the sun is so high in the sky that it creates the exact same angle for both of these guys. So by the angle theorem, we know that these two triangles are similar to each other, but we're going to spend our time talking about sides. So once you build your similarity, you can use it in any kind of way. So I built my similarity using angles, and I'm going to use it for sides. So let's see if we can do that. I'm going to start off by building a set of ratios for my known sides, which is going to be my 48-inch long shadow and my 6-foot long shadow right there. Then I'm going to build another ratio, and this time it is going to be for heights. And this is going to be for my height of my lifeguard and then the height of my chair. And now I can solve this. I'm going to solve this by reducing my first fraction right here. I like to do that right away, and so that's going to reduce down. 6 is a good common factor for 48 and for 6. I like to do this so my numbers are a little bit more easy to work with. Then I'm going to cross multiply. And when I cross multiply, I'm going to end up with 8x is equal to 76. And then lastly, I'm going to divide to solve. And it turns out that the height of our lifeguard chair is going to be 9.5 feet. Now, in the original problem right here, when we were talking about our man, he was measured in both feet and inches because that's what we usually use. And so instead of writing this as 9.5 feet, which I'm okay with, there's nothing wrong with that. You could also take this half of a foot right there and convert that to inches. And you could also say that this would be 9 feet and then 6 inches. Either of these would be great answers. First one's a little bit more convenient and quick, and the second one is a little bit more matching with the way that they presented the information in the beginning. So we use this set of similar triangles to solve for our missing piece. So this kind of brings together what we had talked about in section 8.1 with what we had talked about in sections 8.2 and 8.3. Let's do another one. This time what we're going to be doing is we're going to be solving for a variable, which is going to be x, and we're going to be solving it in a set of triangles that are similar to one another. So we already have similarity built, so we don't have to worry about that. We're just going to see if we can solve for some of those missing variables. So let's do it. To begin with, I'm going to start off the same kind of way I used to start off in section 8.1 by setting up a scale factor. So my k value right here is going to be based off the one set of sides that hopefully doesn't have any variables in it. And I noticed that I've got some x's for these upper left sides, and I've also got these x's for these lower sides. And I'm going to come back to those, but the side that I want to start off with is the sides that don't have any x's at all, which is the 4 and the 10. When I'm building my ratio, I'm choosing to go from left to right and from the small triangle to the big triangle. I'm going to reduce this fraction as well, and that's going to reduce down to 2/5. Okay, now that I've got a working ratio, I should be able to use that 2/5 in order to solve for x. Now, when I'm using this, since these two triangles are similar, all sides are proportional. So even though I have two different locations that have x's in them, I don't need to use both. I can just pick one and use that, and that's totally fine. So I'm going to choose to use the one that looks a little simpler for me. I'm going to use the x minus 3. So I'm going to set my x minus 3 and my 20 as a second ratio. So there's my setup right there. And I'm going to cross multiply. 2 times 20 is going to just be some numbers that I can work with. And my other set is going to be 5 times the quantity of x minus 3. Make sure you're using your parentheses there. So I'm going to simplify a little bit. 2 times 20 is going to give me 40. And 5 is going to get distributed to give me 5x minus 15. I'm going to bring my 15 over with my 40 by adding it, which is going to take me up to 55. And then I'm going to divide both sides by 5. And when I divide both sides by 5, I'm going to get an x value of 11. Now, if you are not convinced, if you're thinking to yourself that 2x plus 3 is important to me and I want to understand how to use it, you will use it in the exact same type of way. I've got my exact same scale factor fraction of 2/5 right there. And then I've set up another fraction or ratio using my 2x plus 3. And I'm going to cross multiply. When you cross multiply this one, you're going to end up with the exact same x value of 11. So both of them are critical, but you don't need to use both of them at the exact same time. You can just use your scale factor and then solve for x, whichever way makes you feel good. All right, here's another problem for you that is all exactly the same. I want you to see if you can solve for x on this one right here. You've got x's down here at the bottom, and you also have x's up here in the upper right, and you have also got some sides that don't have any x's on them at all. I'm going to set my two sides that don't have any x's up. I'm going to set those up as my scale factor ratio, and I'm going to go from left to right again. So that's going to give me 4/12, which reduces down to 1/3. Then from there, then I can set up my fraction using my sides with my x minus 1 and my 18, which is what I've done right here. Or I can use my 8 and my 3 times the quantity of x plus 1, which I have done here. Now, you don't have to do both of them. You can just pick whichever one you like, but I want you to see that you can get the exact same answer for x of 7 for both of them. So it does not matter which one you choose.